Okay, let's dive in. We tend to think of the Earth as, well, rock solid, right? But it actually wobbles.
It does. And not only that, its spin speed isn't perfectly constant either. It varies.
And these tiny, tiny shifts,
Yeah.
they actually have massive consequences over, geological time. We're
Yeah.
talking influencing things like ice ages.
Exactly. It's quite amazing. And the big question, the one we're tackling today based on our sources, is what's actually causing all this wobble, these speed
Right.
changes?
What's behind this sort of celestial dance?
And what's really cool is that by studying these subtle movements, this planetary wiggle and these tiny speed adjustments, we get this incredible window into what's happening deep inside the Earth.
So it's like planetary forensics.
Kind of, yeah.
Yeah.
Tracking these things helps us understand the huge forces at play within the mantle and core.
Okay, perfect. And that's really the heart of this deep dive. We had a listener ask for a rundown, clear but still thorough on why the Earth isn't this perfect smooth spinner. So we've pulled together some really interesting sources. There's even a book that gets pretty deep into the physics, the viscoelasticity of it all.
Right, the mathematical side.
Yeah. But our goal here is to pull out the key insights for you without getting totally lost in the equations. Think of it as your shortcut to grasping the essentials of Earth's rotational quirks.
Exactly. We want to distill the core ideas. What the wobble and spin changes are, what forces are driving them, and crucially, how Earth's internal structure, its sort of squishiness, plays a role.
Give you the big picture on this dynamic planet.
Precisely.
Okay, so this planetary dance.
Hmm.
Where do we start? The sources suggest there are, two main ways the rotation changes manifest.
That's a good starting point, yeah. One way is looking at the axis itself, the spin axis, relative to the distant stars. Does the point in space, the North Pole, aims at drift over really long timescales?
Okay, like where the North Star appears to be.
Sort of, yeah. That's one part. The other way is how the rotation axis moves relative to the Earth's surface.
And that's this polar wander thing.
That's polar wander, exactly. The solid Earth itself is kind of reorienting beneath the spin axis. Imagine the geographic North Pole actually migrating across the Arctic over millennia.
Right, not just the magnetic pole, but the actual spin axis location on the surface.
Hmm.
Got it. Now, a term that comes up immediately is the inertia tensor. Sounds technical.
It does sound a bit heavy, yeah.
Yeah.
But the core idea is actually pretty intuitive. Think of it as just a description of how Earth's mass is distributed.
Like, is it balanced?
Exactly. Is the weight spread out evenly, or is it lopsided? Like spinning a bicycle wheel, if it's perfectly balanced, it spins smoothly. But if you tape a weight to one spot on the rim, it's going to wobble, right?
Right.
The inertia tensor basically mathematically describes that distribution of mass for the whole Earth. Our sources have the specific equations, but the key thing is it's all about where the mass is located relative to the spin axis.
Okay, so if that mass distribution changes, like you mentioned ice ages, huge ice sheets growing
Yeah.
and melting, that must shift a lot of weight around.
Immense amounts. And yes, that's a perfect example. Any significant redistribution of mass, whether it's ice sheets forming or melting, slow convection currents stirring rock in the mantle, even really big earthquakes, it changes that inertia tensor.
And the Earth has to react.
It has to adjust its spin. It's a bit like, a figure skater pulling their arms in to spin faster or extending them to slow down. The planet subtly changes its rotation and wobble in response to these internal mass shifts.
Okay, and this isn't just happening randomly, is it? There's some kind of governing principle.
Oh, absolutely. There's a fundamental equation called the Liouville equation. You can think of it as like the main rule book for Earth's rotation.
The physics behind the wobble.
Pretty much. It connects changes in that inertia tensor, the mass distribution, and any external forces, like tides, to the resulting changes in the Earth's spin rate and the wobble of its axis. It's the foundation for understanding all this.
Okay, now when people talk about the wobble, one specific term always seems to pop up, the Chandler wobble. What's that specific wobble?
Right, the Chandler wobble. It's a really prominent component of this polar motion, this wobble relative to the surface. It's a relatively small cyclical wobble with a period of roughly 433 days.
So just over a year.
Yeah, just over a year. Imagine a spinning top that's not perfectly balanced or is losing a bit of energy. It develops that slight wobble, right?
Okay.
Earth has a similar kind of natural wobble, but it's surprisingly persistent.
And what keeps it going? Or what causes the longer-term drift that this wobble rides on top of?
Ah, good question. That's actually still an active area of research, figuring out exactly what excites and sustains the Chandler wobble. But our sources point to a few key players driving the overall polar motion.
Okay.
A major one, especially for the long-term drift of the pole over thousands of years, is thought to be post-glacial rebound PGR.
Okay, the Earth bouncing back from the ice ages.
Exactly, the slow adjustment of the mantle as it recovers from the weight of those ancient ice sheets. But some newer research, like from 2016 mentioned in the sources, also suggests that ongoing mantle convection, that slow churning of rock, and even the accumulated effect of large earthquakes might also play a role in nudging the pole around.
Interesting. So it's not just one thing.
Basically a combination.
Okay, so we've established Earth wobbles and adjusts its spin because mass shifts around.
Yeah.
But you mentioned the Earth isn't perfectly rigid, it's bouncing back. This brings us to viscoelasticity. Sounds squishy.
It kind of is. Well, not squishy like jelly, but definitely not perfectly rigid like a billiard ball either. Viscoelasticity just means it deforms under stress over time.
Okay.
Think of a silly putty. If you pull it really fast, it snaps. That's like the elastic part.
Yeah.
Solid-like. But if you pull it slowly, it stretches and flows. That's the viscous liquid-like part. Earth does both, just on, much longer time scales, and it's obviously much, much stiffer. This slow deformation and eventual rebound is absolutely critical for understanding how it responds to things like ice sheets sitting on it for millennia.
Right, because the weight presses down,
Yeah.
and then when the weight lifts, it doesn't just spring back instantly.
Precisely. There's a delayed viscous response.
Okay, so how on earth do scientists model that? Something that's kind of solid and kind of flows. That sounds incredibly complicated.
It is complex. One key tool they use is something called spherical harmonics.
Okay.
It's basically a mathematical way to describe complex shapes, like Earth's slightly irregular surface or variations inside, by breaking them down into a series of simpler, standard shapes or patterns. Think of it like building a complex 3D model out of simpler mathematical blocks. Our book source gets into the nitty-gritty, but the idea is to represent the lumpy Earth and its internal layers, different densities, stiffnesses in a manageable way.
Okay, so spherical harmonics handle the shape and the layers. But how do you bring in that time-dependent squishiness, the viscoelastic part?
Ah, that's where some clever mathematical techniques come in, namely the correspondence principle and something called Laplace transforms.
Laplace transforms. Okay, vaguely remember those from math class.
Yeah. Well, the basic idea, without getting too deep, is this. You might know how a perfectly elastic Earth would respond instantly to a force. The correspondence principle lets you use that elastic solution, transform it using the Laplace transform into a different mathematical space, like a frequency domain where the time-dependent viscoelastic behavior is easier to handle.
Okay.
You solve it there, and then you use an inverse Laplace transform to bring the solution back into the time domain. It tells you how the deformation evolves over time, incorporating that slow, viscous flow.
So it's like a mathematical trick to handle the time element.
Kind of, yeah.
Mm.
It lets you leverage simpler elastic solutions to understand the more complex, time-evolving viscoelastic response, like watching a complex process frame by frame to understand it better.
Got it. Okay. Now, another term I saw were love numbers, which sounds a bit romantic for geophysics.
They do have a great name, but yeah, in this context, love numbers, usually written K and H, sometimes with a subscript L or T, are just dimensionless numbers. They quantify how much the Earth deforms under a specific force.
Like how much it bulges from tides or sinks under ice.
Exactly. They measure the Earth's give or response, both the immediate elastic part and the longer-term viscoelastic part, to things like tidal forces from the moon and sun, or the load of a giant ice sheet.
And because of viscoelasticity, these love numbers aren't fixed values, right? They change.
Precisely. The viscoelastic love numbers are time-dependent. Their value depends on how long the force has been applied or how long it's been since it was removed. Calculating them involves that inverse Laplace transform process we just mentioned.
Okay.
And often this reveals that the Earth's relaxation, its return to shape, happens through various modes, each with its own characteristic timescale, its own relaxation time.
So different parts or processes relax at different speeds.
Kind of, yeah. And interestingly, the source material notes that if you have weird situations inside the Earth, like denser material somehow ending up on top of less dense material, maybe due to chemical differences, it can actually lead to instabilities in these relaxation modes. Things wouldn't just relax back smoothly.
Huh. Complex stuff. Okay, so we have the wobble, the spin changes, the Earth's viscoelastic nature. Now let's really dig into the forces driving it all. You mentioned post-glacial rebound, PGR is a big one.
Yes, PGR is definitely a major player, especially for long-term polar wander and changes in Earth's overall inertia budget.
So unpack that a bit more. Ice sheets melt.
Right. Imagine these absolutely colossal ice sheets, miles thick, sitting on places like North America and Scandinavia during the last ice age. That's immense weight pressing down, deforming the crust, and pushing mantle material out from underneath.
Uh-huh.
Then, relatively quickly in geological terms, that ice melts, the weight is removed. But the mantle material doesn't just flow back instantly, it takes time.
Thousands of years, right?
Exactly. We're still rebounding today from the end of the last ice age, over 10,000 years ago. This slow, ongoing uplift in formerly glaciated areas and sinking in areas around them is constantly redistributing mass within the planet.
And that redistribution changes the inertia tensor,
Correct.
which makes the Earth adjust its rotation axis.
You got it. That ongoing adjustment to the removal of those massive ice loads is a primary driver of the observed secular drift of the pole, the long-term polar wander.
Makes sense. Okay, what about deeper forces?
Yeah.
You mentioned mantle convection earlier, that slow stirring in the Earth's interior.
Yeah, mantle convection. This is the super slow circulation of rock in the mantle driven by heat escaping from the core. It's the process that ultimately drives plate tectonics.
Uh-huh.
And because hotter rock is slightly less dense than colder rock, this convection creates variations in density deep within the Earth. These density anomalies also contribute to the overall mass distribution and therefore affect the inertia tensor.
So convection currents could also nudge the pole.
That's the idea. Now, whether mantle convection is a direct driver of polar wander, or if its main effect is more about shaping the long-term structure that then influences how the Earth responds to other things like PGR, that's still somewhat debated among scientists, but it's definitely part of the picture.
Okay, and this leads to something called true polar wander, PPW. How is that different from just the regular wobble or drift?
Right. True polar wander is kind of the grander version. It's not just the axis wobbling slightly relative to the surface. It's the entire solid Earth, the crust and mantle together rotating relative to the fixed spin axis in space.
Whoa. So the whole planet is basically reorienting itself.
In a sense, yes, it's trying to get the largest concentrations of mass aligned closer to the equator, if possible, to be more stable in its rotation. Our sources suggest that TPW might be linked to really major events, like the cumulative effect of ice ages over long periods, or perhaps large-scale shifts in mantle convection patterns. It's a more fundamental rebalancing act.
That's wild. Okay, so we have these huge slow forces. What about sudden things? Earthquakes were mentioned. Can they really affect the whole planet's spin?
Surprisingly, yes, although the effect is tiny. Really big earthquakes, especially those megathrust earthquakes in subduction zones where one plate dives under another, cause significant rapid shifts in mass.
Okay.
The research mentioned suggests there are two effects: the immediate deformation during the quake, coseismic, and the slower deformation that happens between quakes, interseismic. And interestingly, these two effects tend to nudge the rotation axis in opposite directions.
So they kind of cancel out over the long term.
Not perfectly, but they complicate the signal. It means earthquakes cause the pole to sort of wander around a bit in a complex way rather than just pushing it steadily in one direction. It's a measurable effect, though very small compared to PGR.
Still, it's incredible to think an earthquake can actually make the whole planet jiggle its rotation.
It really highlights how interconnected everything is.
Definitely. Now, the sources also briefly compare Earth to other planets. How do places like the Moon, Mars, or Venus behave? Do they wobble too?
Yeah, Section 3.11 touches on that. It's really interesting. Whether a planet or moon experiences significant polar wander depends on several things: how fast it rotates, its shape, specifically how much it bulges at the equator due to rotation, what scientists call the dynamical form factor, J2, and its internal structure, like does it have a liquid core?
So different ingredients lead to different results.
Exactly. Mars, for example, shows evidence of significant past polar wander, but Venus is fascinating. It spins incredibly slowly, and it's almost a perfect sphere. So instead of distinct polar wander like Earth or Mars, it seems to undergo something described as mega-wobbling, much larger, perhaps more chaotic oscillations. The moon's rotation is tidally locked to Earth, which dominates its behavior. So yeah, comparing them really highlights how Earth's specific properties lead to its particular rotational dance.
Okay, so we understand the forces and the mechanics a bit better. But how do we actually see these incredibly small changes? You can't just, put a marker on the North Pole and watch it move a few feet a year, right?
No, not quite that simple. We need extremely precise measurement techniques. One key method is satellite laser ranging, or SLR.
Okay, what's that?
Basically, ground stations shoot lasers up at satellites that have special reflectors on them. By measuring the round-trip travel time of the laser pulse very accurately, we can determine the satellite's position and orbit with incredible precision. Changes in Earth's rotation and gravity field subtly affect those orbits.
So tracking the satellites reveals changes in the Earth.
Exactly. And another huge tool mentioned in Section 5 was the GRACE mission gravity recovery and climate experiment and its successor, GRACE-O.
Grace, right. I've heard of that.
Yeah, GRACE used two satellites flying one behind the other. They constantly measured the tiny changes in the distance between them. As the lead satellite flew over a region with slightly stronger gravity, maybe due to more ice mass or groundwater, it would be pulled ahead slightly, increasing the distance. When the trailing satellite flew over, it would catch up. Measuring these distance changes allowed them to map Earth's gravity field and how it changed month by month.
That's ingenious. So you can actually see mass moving around water, ice.
Precisely. You can track ice sheet melting, changes in groundwater storage, even large-scale ocean current shifts, all by monitoring the gravity field. And that data is crucial for understanding the mass shifts that drive the rotational changes.
And tying these observations back to the Earth's interior,
Mm.
does tracking these gravity and rotation changes help us figure out things like how viscous the mantle is?
Absolutely. That's one of the major payoffs. By comparing the observed changes like the rate of polar wander or the speed of postglacial rebound with predictions from models using different internal properties, scientists can constrain things like mantle viscosity.
So you run a model with a certain stickiness for the mantle, see if it matches reality, and adjust.
Essentially, yes. Section 5.2 specifically mentions how these kinds of observations help tease apart the viscosity of the lower mantle versus the upper mantle, which is a long-standing question in geophysics. The way the Earth responds tells us about its internal resistance to flow.
Like poking the planet to see how squishy it is in different places.
A very sophisticated way of poking it, yeah.
Okay. The sources also mention a longman paradox. Paradoxes are always intriguing. What's that about?
The Longman paradox. It's a bit technical, but it relates to the boundary between the liquid outer core and the solid mantle. Section 1.6.3. Specifically, it concerns how you mathematically handle the conditions at that boundary when you're modeling deformation, especially if the core isn't just a simple fluid but might have some layering, maybe due to chemical differences.
Okay.
Different assumptions about the core and that boundary lead to slightly different predictions for how the Earth's surface should deform in response to loads, like tides. It's one of those tricky details you have to get right for really accurate models.
A puzzle at the core mantle boundary. Got it. And finally, looking forward. What about future polar wander? Are we, like, heading for a big shift? Can we predict it?
While predicting future true polar wander accurately is really challenging, as Section 3.8 notes, realistic models need to consider that Earth doesn't just relax with one or two simple timescales, but has a whole continuous spectrum of relaxation times. That makes the modeling very complex.
So, no easy answers.
Not easy ones, no. However, we know for sure that processes like the ongoing melting of ice sheets in Greenland and Antarctica are continuing to redistribute mass on a large scale.
And that has to affect rotation.
It absolutely has to influence polar wander and maybe even the length of day subtly. The exact trajectory and speed of future polar wander depend on the details of future ice melt and how the mantle continues to respond. It's definitely something scientists are watching closely.
Wow. Okay, well, this has been incredibly illuminating. A real journey from tiny wobbles to deep mantle processes.
It covers a lot of ground, doesn't it?
It really does. So just to kind of wrap up the key takeaways for everyone listening, the big message is that Earth's rotation isn't fixed. It's dynamic.
Constantly changing.
Yeah, and it's influenced by this really complex dance between forces like ice mass changes, that slow churn of mantle convection, and how the Earth itself responds, its viscoelasticity, its squishiness.
Exactly. And things like polar wander and tiny changes in spin speed, they aren't just, geophysical curiosities. They're measurable phenomena.
Right, things we can actually track with satellites.
And they provide these invaluable clues about the Earth's internal structure, its viscosity, and the processes happening deep beneath our feet.
And figuring all this out requires some seriously sophisticated modeling and these amazing observational techniques like GRACE. It really highlights how science is constantly refining our picture of how our planet works.
It's an ongoing process for sure. Our understanding is always evolving as the data and models get better.
It really makes you stop and think, though, how these, seemingly distant geological processes, things happening over thousands of years deep in the mantle, or way back during the ice ages, how they directly connect to something as fundamental as how our planet spins day to day.
It's a powerful reminder of just how interconnected Earth's systems are. Everything influences everything
Yeah,
else.
absolutely. So, a final thought for you to ponder. If this deep dive into Earth's wobble and spin has sparked your curiosity, maybe consider exploring a bit further. You could look into those fascinating love numbers, or dig more into viscoelasticity, or perhaps check out the details of the GRACE mission and the kind of gravity data it collected.
There's definitely a whole world of fascinating geophysics out there if you want to keep exploring.